Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at a certain defect in the rational numbers, which is termed as the incompleteness of rational numbers. Before we get there, let us recap what we did the last time. So last time we defined the abstract notion of a field, and so far the only example of a field that we have is the field of rational numbers. And then we discussed the notion of an ordered field, where you have a total ordering on a field, and this total ordering behaves well with respect to the field operations. So if you have an inequality, then that inequality is preserved when you add a fixed thing to both sides, and the inequality also is preserved when you multiply both sides by a fixed positive thing. So that's what an ordered field is, and again the only example of that we have is so far is the field of rational numbers. Alright, now for the problems. So the one problem that I want to specifically emphasize is this one, which most of us, I'm sure, are familiar with. It's just saying that square root 2 is irrational, but we can't write this so far. I mean, so far what we've developed does not even allow for this symbol as such. So we phrase it this way, that there is no rational such that its square is 2. And I have given essentially the full details, but I encourage you to first try it for yourself and then look at the hint if needed. But this is very important. We'll use this problem in today's lecture. Everything is important. In fact, all the problems are important. Alright, so let us define the notion of an upper bound, and we'll define it in great generality. So let P, P be a poset and S be a non-empty subset of P. An element little p in capital P is said to be an upper bound. It's called an upper bound of S if the following happens. So basically P is an upper bound of the set S if every element in S is smaller than P. Alright, a very simple definition. And let me quickly give an example. It's a very simple example. So let S be this 3-element set, which we are thinking of as a subset of the natural numbers. So our poset here is this natural numbers with the usual ordering. Then 10, for instance, is an upper bound of S. In fact, even 3 is an upper bound, because 3 is greater than equal to everything here, so even 3 is an upper bound. Alright, note that upper bounds may not exist. So for example, one example is if S is the set of all prime numbers, then S has no upper bound in N. This is equivalent to saying that the set of prime numbers is infinite, which is a theorem due to Euclid. So that's that. Or we could have taken just the set of natural numbers itself, that as a subset of the set of natural numbers, meaning n as a subset of itself is also a subset which is not bounded above, does not have an upper bound. Right? So very simple things. Similarly, you can define what is called a lower bound. So I will leave that to you to define for yourself. Lower bound. So let me say it in words. So suppose you have a subset S of a poset, then you say that little p is a lower bound if the reverse happens. Okay, and the same kinds of comments hold. You can find examples of subsets of integers which do not have lower bounds. Any subset of natural number will have a lower bound. 1 will be a lower bound of any given subset of natural numbers, but for integers you may have subsets which do not have lower bounds. The set of integers itself, for instance. Alright. So now the concept of the least upper bound. This is a very important concept. So this time again we have a poset. I will define it and create generality. So let P be a poset. And S be a non-empty subset. Non-empty subset of P. We say that P is a least upper bound. So right now I'm saying a least upper bound. Least upper bound also abbreviated as LUB of S if two things happen. First of all, it should be an upper bound. P is an upper bound. Of S. And the second thing is that it should be smaller than every other upper bound. So if Q is any other upper bound, of S, then this happens. So it's a natural definition of a least upper bound, but then I'm using an indefinite article, the indefinite article here, but the point is that least upper bounds are unique if they exist. So note least upper bound how do I say it? Least upper bounds are unique if they exist. This is immediate from the definition, because if we had two different least upper bounds, P and P primes, by the virtue of the fact that both are in fact upper bounds, we have both of these two things hold because of the second axiom. Or not the axiom, I shouldn't call it an axiom, the second clause in the definition of a least upper bound. So they are unique. There is only one least upper bound if there is one at all. So I will not use the indefinite article, I'll use the definite article. The least upper bound. Alright, so we have defined least upper bound. Similarly, you can define for yourself a greatest lower bound. Also abbreviated as GLB. So it is first of all a lower bound, and it is such that whenever you have another lower bound, let's say Q, then P is at least as much as Q. It's just the opposite. Alright, so very simple things. And now the point is that you can have a poset where you have a subset which has an upper bound but it may not have a least upper bound. In fact, we'll show that there is a subset of rational numbers with that property, and this is a very important fact. This is the reason why we need real numbers. So let's get there slowly. So consider the poset Q with its usual with its ordering as we defined in our lecture on rational numbers. And now consider this set. What is this set? This is the set of all those rational numbers which are positive, but their square is at most 2. So first, clearly, S has an upper bound. As a side remark, when something has an upper bound, we also say that it is bounded above. That's another way to say that it has an upper bound. So clearly S has an upper bound, namely if you take even 2 or 3 is an upper bound to S, because if some rational number has a square less than 2, then that thing cannot be greater than 3, right? Everything here is at most 3, in fact at most 2. So this is clearly bounded above. But very important, we will show that S does not have a least upper bound. Does not have a least upper bound in rationals. Okay, so one way to do it is via contradiction. So assume on the contrary that S has a least upper bound, and let's say M in the rational numbers is the least upper bound of S. So suppose it has a least upper bound, and let us call it M. So there are 3 cases. Case 1 is that M square is less than 2. The other 2 cases would be M square equals 2, and the other case would be M square greater than 2. There are only three cases possible. So let us first contradict the first case. So since it is a rational number, and note that it has to be positive. If you take an upper bound of this set, it is positive. So let me just note here that this has to be positive. It cannot be a negative number. So let M equals A by B, where both A and B are positive. Are positive natural numbers. Okay, and let M square, or rather 2 minus M square be equal to C by D, where again C and D are both positive natural numbers. So by assumption that this is the case, this is a positive rational number, and hence we can write it as a fraction where both of these are natural numbers and both of these are positive. So we haven't said much so far. And now let n be a natural number, n be some positive natural number, and just consider this. We'll do something, just play along. So we are considering this number, and what is it? If we do the algebra, we get this is equal to that, which implies that 2 minus this guy is this, right? So far just algebra. So continuing we get this is equal to c by d. Why c by d? Because this is c by d minus this thing. Okay, so what are we trying to achieve? What we are trying to do is we will show that there is a suitable choice of n for which even this is smaller than 2. Once we indeed achieve that, this number would be in S. But this number is indeed, or rather I should say, this number is greater than m. But that would be a contradiction because m is supposed to be an upper bound. It's by our assumption the least upper bound, but at the very least it is an upper bound of S. So this guy should this guy should not be smaller than 2 for any n. So that is the strategy. We'll show that there is a suitable n. In fact, for all large enough n, this will be at most 2, and therefore we'll get a contradiction. So we'll do that properly. All right. So how do we do that? So let n equals 4AD. This is an overkill, but it does the job. Then c by d minus 1 upon n square plus 2m upon n equals c by d minus 1 upon 16 a square d square plus 2a by b times 4ad. Just replaced n by 4ad. That's all that we did. This becomes that, and this okay, so I also replaced m by a by b and n by 4ad. So just some mindless algebra so far. So this is equal to let's check if this is true. Yeah, a cancels out, and yeah, so we get this. Yes. So now I take 1 upon d common, get c minus 16a square d plus 1 upon 2b, and this thing is strictly greater than c minus half plus half. Let me use a different bracket. So why is that? The thing is that this thing is strictly greater than, half is strictly greater than that, and there's a minus sign, so someone can basically figure out that this is a strict inequality and not just an not like this. It's strict. Okay, but now this is equal to c minus 1 upon d, which is greater than equal to 0 because c is a natural number. So what this shows is that this thing is strictly positive because there's a strict inequality here. So this thing is strictly positive, which is nothing but that thing. So which means this thing is strictly positive. So therefore, for n equals 4ad, we have this guy 2 minus m plus 1 upon n whole square is strictly positive, which implies that m plus 1 by n whole square is less than 2, which implies m plus 1 by n is an S, but that implies that m is not an upper bound of S, and that's a contradiction. We started with the assumption that m is in fact the least upper bound of S, but what we've concluded is that it is not even an upper bound of S. So we have a contradiction. So this case is simply not going to hold. The second case is equality, that m square equals 2, but we just mentioned in the problems that this is not possible. In fact, there is no rational number whose square is 2. That's exactly what the problem said. So this is also a big no. So we have contradicted the first one, we have contradicted the second one. Now for the third one, this is very, very similar to the first one, so I will not give the details, but let me mention the fact. So it is that m square is greater than 2. So here we can find a suitable n such that m minus 1 by n whole squared is greater than 2. It is just like in case 1. The same kind of calculation will give us that. So once we have found such an n, we have a problem, because then m minus 1 by n is an upper bound, but then m minus 1 by n is an upper bound of S, which is smaller than m, which is strictly smaller than m. This is a contradiction to the fact that m is the least upper bound. Here we are able to find another upper bound which is smaller than m, so m cannot be the least upper bound, so we get a contradiction, and therefore no matter what happens there is a contradiction. In every case there is a contradiction, and we are done. So this proves that S does not have a least upper bound. In the rationals. Okay. So basically there is a defect in the field of rational numbers. There is not a defect, but there is some kind of incompleteness that's lingering in the field of rational numbers, and this is the reason why we need something more perfect than the rationals. There are these weird gaps left around in the rational number field, and this is what motivates the notion of the real numbers. Basically, in the next lecture we'll see a proper definition. Basically we'll say that it is a totally ordered field which does not have this problem, where if something has an upper bound, it also has a least upper bound. That's basically what a field of real number is. It is not clear from the definition that such a thing even exists, let alone uniqueness. So that will be the subject of further discussion. But for now, let me just make a comment and end the lecture. It's basically that every totally ordered field contains the rational numbers in a natural way. So here is what I'm trying to say. So let F be a totally ordered field. Sorry, what am I saying? Is it be an ordered field? This heading is wrong. Be an ordered field. An ordered field is by definition totally ordered as a poset. Be an ordered field. So so 1 is obviously a member of F. It is the multiplicative identity. 2 by definition is 1 plus 1. This is also in F. And 3 is by definition 2 plus 1. So all of this is happening in F. Don't think of them as natural numbers. So they behave exactly like natural numbers, but all of this is happening in F. This is an F, and this is the way we define these numbers. So what I'm saying so far is that the natural numbers have a quote-unquote natural, no pun intended, identification within the field F. And this identification carries over all the order properties and all the algebra. So if you add two things in the natural numbers and then take this image of that guy in F, meaning the corresponding element in F, or you first take the corresponding elements in F and add them, it doesn't make a difference. So there is this natural copy of natural numbers, no pun intended, again, in any given ordered field. And similarly, one can in fact have a copy of rationals. So first let us see what about integers. So we have defined 1, 2, 3. Similarly, of course, 0 is already there in F. This is the additive identity. And minus 1 is minus 1 times, or it is the additive inverse of 1, and minus 2 is the additive inverse of 2, and minus 3 is the additive inverse of 3, and so on. So basically now you will see that if you consider this set in F, this looks like exactly like integers, but this is in F. So integers can be naturally identified as a subset of this given ordered field. Basically, n in Z is identified with n in F, and this looks silly, but this is a meaningful statement. And this also carries over the algebra and the order properties. Basically, if you take two integers and add them, and then take the image, or you first take the corresponding elements in F and add them, you get the same thing. So this respects the algebra as well as the ordering. So if m is less than n in integers, then the same thing is true for the corresponding elements in the field F. And what I really want to say is that this carries over for the rationals. So here, each of those things, if you take A and B, where B is non-zero, you pick some A from this set and some B from this set where B is non-zero. This makes sense. You can divide things in a field. This is basically B inverse times A, and that's what we write in this way. So this can be identified with the rational number A by B. And that way one gets a natural copy of the rational numbers in any ordered field. And again, this also preserves the algebra as well as the ordering properties. So every ordered field has a natural copy of the rational numbers built inside it. Right? So next lecture we'll define real numbers. So it will be an ordered field with a certain completeness property, which I hinted at in the previous slide. And this already quote unquote contains the rational numbers, and all of this containment and identification business we forget about. We just just think of R as something which contains rational numbers. We don't have any kind of identification thing going on in our heads. It's understood what we are doing. So anyway, all of this will make sense slowly. So I guess this is all that I wanted to say in this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.